Alright, so combinations of combinations. What do I mean by that? Well, that's a combination, and we know it can be either way, and that's a combination. So they have to work together to have our output Q working, as it were. So how do we represent this circuit as an expression, a Boolean expression? Well, we know X is in the equation. It has to be in the equation because the supply has to continue down one of these routes. So X has to be in the equation. Alright? We know that either Y or Z has to be in the equation. So it's going to be X and Y to light that up, or X and Z to light that up. It's X and Y, or X and Z. You could put brackets around these. Okay, so Q is on when these conditions have been met, and hence Q equals X and Y, or X and Z. And we write it like that. The full stop represents the and the plus represents the OR. Logic gates types, we've been through that. We've done AND, OR. We're going to do not NAND nor an XOR, and we're going to look at XNOR gates as well. Right, gate shapes. Our logic gates are represented by shapes. This is AND. The way I remember it is it looks like the D of AND. This is OR. I could draw an OR, O there. This is NAND. It's the opposite of AND. It's negative AND, or inverted AND. And any inversion has a little circle after it. This is OR with a circle, so it's negative OR, or inverted OR. And this is just a NOT. Okay? And this is exclusive OR. It's looking for just one of those to be a 1, or closed, or on. Not both. So exclusive OR. That's dead easy. That is dead easy. In fact, all of this is a lot of fun and dead easy. We're going to look at exclusive NOR, which has this little exclusive double line and a negative, an inversion, and it's written like that. That there is a little plus sign with a circle around it. We've got a cheat sheet. I hope this helps you, or take any one, so our three burgers, and take only all of our variables being 1, so take only ones, one big fat burger, and NOT is just completely invert. It's known as the inverter gate, and NOR is the opposite of OR. Have I got NAND? Yeah, I've got NAND. NAND is the opposite of AND. So I've got a little example here where you've inputted A and B. You've got an AND gate diagram, and you've got a little circle there, so we know it's the inversion. So let's have a look at this. That's definitely not an AND, alright? Because an AND would be 1 if it was if both the inputs were 1s. So this looks exactly like an inversion. And what's our inversion gate, our negative gate? That shape. So actually, that is simply an AND that's completely inverted. Look at our exclusive OR. It's called the exclusive one. The exclusive one means we're looking for 1 only, and so it's an OR table, but only looking for 1, exclusively looking for 1. In the exam, I bet you they will give you A, B, C. I'll bet you they'll give you 3 inputs, 3 variables, and you'll have to do an exclusive OR. Guarantee it. They're always going to throw that into your equation when you have to work out the expression. But just remember, treat it like an OR, but you can't have an output of 1 when you get all 1s. You can only when there's 1 1. And one more is XNOR. Now, I was looking in the textbooks, not much on this, and not much in a previous an exam 3 years ago, but certainly in a recent exam they alluded to this. And this is simply, once again, we're looking at the opposite of our NOR. The equivalent gate is an exclusive OR inverted. And that's what we've done. Can you see that we've inverted that? Alright, the moment of truth. That's not an English expression. The moment of truth is an English expression. But let's have a look at truth tables. I like to put them all together, and as soon as I get a logic gate in an exam, if I was you, I'd quickly sketch something like this, depending on what your variables are, just to have a truth table as the standard and, or not. And is represented by the dot, or by the plus, and inversion, or not, with a line above it. So, the and is only one, the or is 3 ones, and the not is the inversion of whatever variable it is, and this is an inversion of A. That's NAND and NOR, showing you NAND and NOR, and if you want to know, well, it's going to be the opposite of that. So 111 and 0, that's 1 0 and 3 1s, so this is going to be 3 zeros and 1 1. Look how it's represented. This is now coming into our full expression, our full Boolean expression. So A and B with the inversion line above it. This is how we represent XOR. It's got a circle around the OR, the plus. And it's called exclusive OR. I've seen it written XOR, one word, EX-OR, exclusive-OR. So be aware of that. But that's what that is. A reminder of our gate shapes, because we're going into some exercises. You can pause at the stage and then we can move on. There's our AND gate. Quick recap. That's our input, that's our output. A dot is used to show the AND. We've been through that. Sometimes it's omitted altogether, by the way. And AB is also A and B. Remember, a digital device decides I can only combine according to what I receive. If I receive noughts, then I will combine these as an AND combo, if I'm told to. And here we're being told to. This is the OR. A plus sign is used to show the OR operation. These are just reminders. We've been through this. How daft, a plus sign. Actually, not daft at all. Look at the next presentation to do with Boolean equations. It's completely understandable. Okay, completely understandable, because if I had to add the zeros here in a Boolean equation, I would get 0. If I were to add this, what would I get? 1. If I had to add this, what would I get? 1. If I were to add this, I would get 0, but I'd have to carry the 1, and an electronic circuit would have to take it as a 1. So, not so daft at all. This is total inversion of the input A. We've been through that. Oh, sometimes they put an apostrophe before or after, but I haven't seen that in your exam. That's how it's represented. The NAND gate, A and B, with an inversion line above it. The NOR gate, A plus B with an inversion line above it. Exclusive OR gate, just looking for the instance of 1. XNOR, exclusive OR gate, there and there. Exclusive NOR gate, just in case they throw it in. Alright, I've got a little exercise for you to name the gate. Could you try that? Pause and try to test your knowledge before we move on. And I hope you got them right. Now, true to form. True to form. Try it. Could you now give me the output results, taking inputs A and B as an AND, a NAND, an OR, a NOR, XOR, an exclusive NOR. Oh, and I didn't hide that one from you, did I? Inverting A. Pause it and try it, and then check your answers. Right, electronics, and this is the OR. This is great, because this is just showing you how it actually works. So an OR gate will give a high output if any of the inputs is high. For example, what we mean is on. For example, in a simple lighting circuit with two switches in parallel, that's what I wanted earlier, switches in parallel. The lamp will light if either switch is pressed. Now we need to talk about De Morgan. Alright, imagine you had male or female, okay? Now do something when the answer is not male or the answer is not female. So do something when the answer is not M, okay, or the answer is not F. Have a look there. Is there not M and not F? Yes. De Morgan said when you get these combinations, they're actually equal another connective. They are equivalent to another connective. That expression there is the same as saying M and F. So actually our truth table, when we say not M or not F, it's the same as saying M and F. So De Morgan said, he said not A or B is the same as saying not A and not B. Okay? Not A and B is the same as saying not A or not B. De Morgan said an expression said one way is equivalent to the negative statement of that expression, or the opposite connective, one should really say, and inverting the connective, so the or becomes an and. So De Morgan's law, number one, x plus y plus z plus whatever plus whatever plus whatever is the same as inverting those particular variables and changing the expression and. Alright? And x and y and z is the same as inverting each variable and changing the connective. And we put a line on top of it because it's the entire expression is inverted. And to or to and. State of each variable is inverted. The state of each variable is inverted. And indeed the expression carries a line. So that is equivalent to inverting our A and B, negating our A and B, and popping it through an OR. So our AND becomes A and B, and then inverting it, we put the line above it, but it's exactly the same as inverting each individual variable and putting it through an OR. Okay, so AB, negated, is the same as saying individual A inverted or individual B. And just showing you, I suppose it's nicely done. That's our AND with negative, so it's a NAND. And this is the truth table of a NAND, A and B. De Morgan's law, number two. Let's just recap. We've been through that, the inversion. So let's have a look at this. P and Q is exactly the same as saying P, individual P inverted or individual Q inverted. Notice we don't carry the line over or, because this bracketed equation shows me the entire equation should ultimately be inverted once we've changed the operators. And P or Q as an entire expression becomes individual P and inverted and individual Q inverted. P and Q inverted is inverted P or inverted Q. P or Q inverted is inverted P and inverted Q. Well done. You're saying the right stuff now. Nobody's named him as yet, as of today. So no one's seen that there's a competition to name him. De Morgan's laws, summary. Logical connectives change. And to or to and. I've just typed up what he said. So I've just typed that up, so if you want to pause that, you can read it. Come on, let's try a question straight from your textbook. I've said tontos. He said tontos. Why can't they just say work out Q? Look at how they put this. Express Q in terms of Boolean variables A, B, and C for the arrangements of logic gates in the figure below. Work out Q. What is this? Well, step by step, I'm going to show you, pause it and try to do it, and then I will show you step by step. I mean, obviously, you would start with, oh, this is an AND. So A and B is the result of this gate. So you would write A and B there. B is completely negated. Alright? So if you had a table in your mind, that would be 1 and 0. That will be completely inverted. C goes straight into an OR, okay, and you start collecting up the results of each gate. Alright, so have a look here. Inverted B. A and B. Look at that, that's a connection there. So we've got B feeding into there, we've got C feeding into there. So I would do that first. Alright, so it's inverted B or C, and this is the result of A or B, sorry, A and B coming in, but this is turning the entire expression into or inverted B or C. Right, and look what's happening at the end. We negate the entire thing. We negate it with a line above it. So that's our result. I've typed it up there. That's how you express it. However, they want you to do it in its final form, which is that. So A dot B, A and B, plus OR, and that final expression that came through that gate there. And I've bracketed it because you can see we've got a level there. If you can look at this in terms of levels, sorry, a level there, and this middle part is actually that OR. So we've ended up using brackets. In an exam, would you get marked down for leaving out those brackets? You do often get 4 marks for a question like this, sometimes more, sometimes a little less, but I can't imagine if you wrote it like that you'd be completely marked down, possibly if somebody's fussy, yeah. But anyway, let's move on to this question. I've had to rewrite this because the Caboodle textbook had it done wrongly. And sure enough, Caboodle got it wrong. Construct a logic circuit using only NAND gates for the Boolean expression. And this one is construct a logic gate using only NOR gates. We call these logic parameters. Logic parameters. You are only allowed to use NAND gates for your entire diagram. Let's see how it's done. Well, construct a logic circuit using only NAND gates for the Boolean expression. Now, doing this with one of your fellow students in class, he worked backwards, and that's exactly how I work. I prefer to work it out backwards, but let's work it out forwards as normal people do. Right, so we're moving. Our first NAND inverts the A, alright. Our second NAND, on the same level, inverts the B. I would have perhaps drawn this outside, but they don't like your connectors, your circuit lines to cross over, that's why. So we've got a separate A being inverted. Why? Because that's a separate A being inverted. You say, oh, what about that long line? As soon as you see a long line like that, or even 2 or 3 long lines, you know that's towards the end of the entire equation. So we've got a NAND, so it's an inverted A, inverted B. Okay. Now we've got another NAND, so that's the big line, A and B. And here we've got another A coming through, and another B coming through. Okay, and those are inverted. Alright, and let's move on. And here we have the result of these two being drawn up in the equation. Okay, we know that when we put 2 minuses together, it becomes a plus, as it were, if you want to think of it like that. So we've inverted it, and now we're inverting it yet again, so we lose that chappie. And that's our final logic gate that turns it into that expression. Now, question 9 from the textbook says, use NOR gates only. And I'll go through this one quickly. I'm aware this presentation's been quite long. So pause it, work it out on paper, giving you the first bit there. Let's see how we go. Inverting our ORs. It's all about inverting those inputs, and if 2 inputs or 3 inputs come into one gate, remember the entire expression has the inversion line, the negative line. Have we ended up with the correct result? Yes, we have. Apologies, my lines are slightly out. They should be above the letters, not over the brackets. Hope you got that. That one was actually, I found it to be easier than the previous one, but anyway, it just all depends how your brain clicks to these things. But come on, it's a lot of fun. Right. So, at the end of this, you should now be familiar with all of the connectives, the gates. Can you determine the output of a simple logic gate circuit? I'm sure you can do the simple ones. Can you do complex ones? I'm sure you can. Can you use De Morgan's laws to simplify Boolean expressions? Try to memorize them. There's only 4 things that you have to remember for De Morgan's law, and they're 7 slides back. Can you construct a logic gate from the output expression and within given parameters? That's what we've just done in the last 2 exercises, question 8 and 9. I just added in an appendices. Appendix 1 was just explaining about signals, if you need to read about that. And this was a summary of what an input is when we go through a circuit and how it activates an output. And this one is all about electronics, just a summary of basic electronics and binary. And I think that's it. Yes, it is.